Okay, so this is going to be a brief overview on what a derivative is. So, as you'll learn later in math, but this is just like a quick crash course, a derivative of a function is another separate function describing the slope at any given x in the original function. So if this is f of x, the derivative of this would be a function describing the slope at this point and the slope at this point. And if you look, since it's not a straight line, the slope is constantly changing. So it's easier to look at derivatives by starting with a straight line. You think, the slope of this, it's about 1. Because for every time x increases by 1, y increases by 1. So the derivative of this, a function describing the slope, would be y prime equals 1. For example, a more complex one, this is a sine function. This is y equals sine of x. The slope at a turning point will always be equal to 0. And you can kind of guess the slope at other points. This one would be about 1, this one would be about -1. So you can write an equation that defines the slope at these points. The slope at this is 1. So when x is 0, the slope is 1. The slope here would be 0. So when x is this arbitrary number, the slope would be 0. Likewise, -1, etc. You can draw a function like that. This function describes the slope of this function. So, what does that look like with physics applications? So you'll probably see position functions that look approximately like these. It'll either be not moving, always at the same location. It'll be moving constantly with the same velocity. This one means it's always going the same speed. And this one, look, it's speeding up because it moves a little bit in the first second, and then in the next second it moves a little more and more and more continuously. So, how do you find the derivative of these? Well, you look at this one. What does the slope look to be? Since you can calculate it using algebra, you can use your y2 minus y1 over x2 minus x1. Or, that's also known as delta y, which means change in y over delta x. So, if you look, this is 1, 2. Right here, the x position is 2, and the y position is 1, 2, 3, 4. So that means 4 minus, this y position is also 4, over 2 minus 1. So that, as you can tell, you knew the slope was 0. So, because this is not changing, this is a constant position, the derivative of this is 0. Y equals 0. That is what happens when you have an object that is not moving. Now, if an object is moving constantly in a straight line, you can look at this, and anyone who's been through Algebra 1 knows that the slope, that this line, the equation defining is y equals x. So what is the slope of that? Y equals 1x. The slope is 1. So the derivative describing this function is y equals 1. Because you know every time it changes by 1x, it changes also by 1y. So it gets a little overwhelming when you get to quadratic position functions, when it's got a constant acceleration, and because the velocity keeps increasing. Well, this one's a little harder to look, but this is also a familiar function. The equation describing this function is y equals x squared. So how do you find the slope of this? Well, after you learn the power rule, it's easy, but just using this, you kind of have to eyeball it. So this, if you look here, that's the turning point of the equation, because it goes both ways. So whenever you have a turning point, this, like I said earlier, the slope's going to be 0, but here, it'll be about 2, and here, it'll be about 4. So if you were to redraw this over here, an equation of the slope, at time 1, you got 2. The slope's 2, so you have 2. At time 2, the slope's about 4, so you've got 4. So if you look, that's a straight line. Y equals 2x. So if you look, it drops a power. Every time you take a derivative, if you're taking the derivative of x to the 4th, the derivative will be x to the 3rd and other stuff. It drops a power. So, what is the power rule? Well, this is an easier way to look at derivatives. This is the general formula for doing it, but it's a little overwhelming to look at, so we're going to take it apart piece by piece. So if you've got y equals 3 as your original function, as we said on the previous page, if it's a constant, the slope's going to be 0. But why? Because if we rewrite this equation in terms of x, it would be y equals 3x to the 0th. So since x is to the 0th, you multiply. This says you multiply the power to the coefficient, and then you drop the power. Well, if you multiply 0 by 3, you're going to get 0, so that's y equals 0. So it's more obvious in like this one what to do. Because you know from algebra 1 that the slope of this line is y equals 2. That's the derivative function. However, using the power rule, we've got 2x to the first plus 1x to the 0th. Multiply this 1 by the 2 and subtract 1 from the power. So you've got 2 times 1 times x to the 0th. And since x to the 0th is 1, that's also 1. So 2 times 1 is 2. And you can do that to each individual term in the equation. So if you got multiple ones, like this one right here, you just have to do the power rule for each individual one. So you've got 4x to the 5th. Well, you take the 5, multiply it. So you've got 20x, don't forget to subtract 1 from the power, to the 4th. And then, let's look at the cubed one. So, what would you do? You take the 3, bring it over to the 2, subtract 1, you've got 6x squared. Likewise, for this, same thing, plus 2x, and for this one, the power of x is 1. So you multiply it by 1, drop a power, so it's minus 1. And if you look, the power of the derivative is 1 less. So that's a really brief overview of derivatives, but it should be enough to help with the problem. So for the problem, you're also going to need to know integrals, which sounds daunting, but it's just the inverse of the derivative. So if the derivative, you're taking the slope of the function, this one, you're taking a slope function and finding the original. So this notation's overwhelming, but every time you see a tall s, that just means find the integral. So in this case, you're doing the exact opposite of the derivative. So if you're taking y equals 2, you have to add, that's 2x to the 0th, right? You have to add 1 to the power and divide by the new power. So that means y equals 2x. But if we're looking at derivatives, when you have the slope, let's say you have the slope of y equals 2x plus 4 and y equals 2x plus 5. The slope of both of these is going to be y equals 2. And the constants are dropped. So you never know if there's going to be a constant on an integral. So you have to add plus c right here. This means you're saying you don't know what the original start is. So you just have to guess. So the integral of an equation would be, after solving it, you've got to add a plus c. Likewise for this one. You have to add a power, right? So x2 plus 1 divided by this new 2 plus 1, which is x cubed, that's ugly, but x cubed over 3. Integral of 0, well, you have 0, x to the 0th, add 1 power, divided by 0 plus 1. You've got integral of y still equals 0, can't forget the plus c. So integral of y equals any constant. So the derivative of any constant is always going to be 0. Likewise, if you've got 0, it could be any constant. So what's the practical use of integrals? Well, first, we're going to solve a couple using graphs, which is way easier than using that rule. So you've got this function is y equals 1. So, well, using the rule before, if y equals 1, then therefore f would be y equals x. So this is the original function. However, you can find that using area. So it's a little wonky to think about, but the area under a graph at a specific time is equal to the displacement. So look, we've got 1, 2, 3, 4, 5, 6, and 1. So the area under this graph, you just compute it like you would in geometry, is 6 times 1 or 6. So the y value of the original function, not the integral, not the derivative, but the integral of the derivative, would be 6. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Look. So that's how you find total movement along y using an integral. So in this one, f or y, they're interchangeable, y equals 2x, so that would be x squared. To find a location, okay, let's say we want 2 seconds. We want to know where this one is at 2 seconds. So we compute the area. Look, this is just a triangle. 1, 2, 3, 4. So 4 times 2 times 1/2 equals 4. So at time 2 seconds, it'll be at 4. 1, 2, 3, 4, and there it is. So, in application to the motorcycle problem, if you want to find total displacement from where it starts, you just have to find the area under the entire curve. This is the end goal of your motorcycle problem or the Harley problem. So, if this is the derivative function, then remember, if you're trying to draw the original function, you have to increase the power. So if this is a straight line, then it would be kind of quadratic going up because the slope's positive. And then, but as the slope starts off small, the slope's it starts off at rest and it's increasing. And then once you get to the top, it's a flat line at 3, right? That means you've got a line with a slope of 3x. I'm not going to draw it to scale because I don't have room, but you got an upward sloping line. And here, since it's sloping down, you're still covering more area. Even though it's slowing down, you're still covering more area. So it's going to be a quadratic going the opposite direction. Look, it starts off slightly more steep and gets less and less steep. So this would be how you draw the position function of the motorcycle. I hope this wasn't too confusing. It's a lot of math in a very short period of time, but I believe in you guys. And also, besides memorizing the kinematic equations, always remember acceleration is the derivative of velocity, which is the derivative of position, which means position is the integral of velocity, which is the integral of acceleration. Have fun, guys.